This is lesson 19 of our semester-long video sequence on basic circuit analysis. Lesson 19, superposition, source transformation, and Thevenin and Norton revisited. Whew, if that seems like a lot, well, it is. But the idea is that you understand these, at least in concept, from their DC equivalents back earlier in the semester. So you've got the ideas, that's the assumption, and now we're just going to work on the mechanics using complex numbers and apply them to AC circuits. So we're going to go a little bit quicker than we did previously with DC. So we'll start with superposition. Now in DC circuits, you could use superposition more or less like a trick to solving a circuit. If you had more than one source, you could determine the contribution of each source to the output and then add up all of those contributions and you would have the total output. Okay, so here we have three sources. You could turn off the other two, find the output, then repeat for each source, leave each source on, find the output, and then add them all up. So again, in DC that was kind of a trick. You could use it if you wanted to, or you didn't have to. In AC circuits, the difference is that if you have multiple sources, you have to use it. You have to use it if the multiple sources have different frequencies. So here you see we have a frequency of 2 radians per second, 5 radians per second, and a DC source which has a frequency of 0. You have to use it because you're going to transform this into the frequency domain picture. And remember that the impedance of the capacitor was 1 over j omega c, where omega is the frequency. And the impedance of the inductor is j omega l, again where omega is the frequency. So when you transform this picture into the frequency domain, which frequency will you use? Will you use 2? Will you use 5? Or will you use their DC equivalent when omega is 0? This is, I'll write this here. This is basically omega is equal to 0. Notice when omega is 0 here, the impedance of the capacitor is infinite, an open circuit. And when omega is 0 here, the impedance of the inductor is 0, a short circuit. So which will you use? Well, the answer is you have to consider each one separately, each one of the sources separately. So let's do that. Let's just consider the 10 cosine 2t source. All right? So we're going to keep that guy, and we're going to transform this into the frequency domain. So we're going to say 10 angle 0 degrees volts. Right? Now, instead of labeling 2 Henry, the inductor 2 Henry, here we're going to find that the impedance of that inductor is J times 2 radians per second times L, which is 2 Henry. So this gives us J4 ohms. Okay, the current source is an open circuit. Turning it off. No current flows. Open circuit. The resistor is still just 1 ohm, and here I'm not going to call this V out because V out is with all three of them turned on. I'm going to say that this is V out prime. Now the capacitor, 1 over j omega c, so this is 1 over j times, again, 2 radians per second times 0.1 farads. So this is 1 over 0.2, right? So 1 over 0.2 is 2 tenths, excuse me. 2 tenths or 1/5, so 1 over 1/5 is 5. Bring the j up, this is minus j5 ohms. Minus j5 ohms. We've got the 4 ohm resistor, We're going to turn off the voltage source. Turning off a voltage source, 0 volts, makes that a short circuit like that. Okay, so now we got to try to get this V0 prime based on this picture. Notice now that the negative J5 ohms and the 4 ohms are in parallel. So the negative J5 ohms in parallel with the 4 ohms, okay, that makes the product over the sum. So that makes negative J20 over 4 minus J5 ohms. That comes out to be, so if we multiply that by the complex conjugate of the denominator, then the denominator becomes purely real, and you'll see that we get 2.439 minus J 1.951 ohms. So that's the equivalent impedance of this parallel part of the circuit there. So now we have, considering these two components to be 1 of equivalent impedance, this guy, we have a series circuit then. We have the voltage source in series with J4 ohms, in series with 1 ohm, in series with the combination. So we can get V0 prime using voltage division. V0 prime equals 10 angle 0 volts times the impedance whose voltage I want, that's the 1 ohm, divided by the sum of the 3 impedances. So that's 1 ohm plus J4 ohms plus the equivalent 2.439 minus J 1951 ohms. Okay, so you can combine the real parts in the denominator and the imaginary parts in the denominator, multiply by the complex conjugate over the complex conjugate. What you find is that V0 prime is 2.498 angle negative 30.79 degrees volts. So we'll just box that up and we'll come back to it. Actually, let's write it in the time domain then. V0 prime is 2.498 cosine, because I started with a cosine, the frequency doesn't change, and the phase is minus 30.79 degrees. Okay, we'll put parentheses around that. Volts. So here's what we want. Back in the time domain. Again, feel free to pause the video if need be, but I'm going to erase this to make some space. And we'll just keep the answer hanging around there. Okay, I'll move it there. Alright. Now, so that was the contribution just due to the 2 rad per second source. Now let's find the contribution due to the 5 rad per second source, the current source there. So let me redraw this picture. Turn the voltage source on the left off, so that becomes a short. And the inductor now, I'm going to erase this. The inductor now is J times 5 rad per second, because this is, we're going to consider only the 2 sine 5t source. Okay, so the impedance of that inductor, that's J times 5 rad per second times 2 Henry. Okay, that's J 10 ohms. So I'll label that here, J 10 ohms. Here's my current source. So this is 2 angle 0 degrees amps. Here's the resistor. The resistor is still just 1 ohm, and the voltage across it, I'm going to call that V0 double prime. Now the impedance of the capacitor, 1 over J times 5 rad per second times 0.1 farad. So 0.1 times 5 is 0.5, or 1/2. 1 over 1/2 is 2. Right, so bring the J up, this makes minus J2 ohms. Minus J2 ohms. 4 ohm resistor doesn't change. And then again, the voltage source turned off is a short circuit. So now we're looking for V0 double prime. Alright, well then, again, these two guys are in parallel over here on the right. So let's find the equivalent impedance of negative J2 ohms in parallel with 4 ohms. So that is the product over the sum. That's negative J8 over 4 minus J2 ohms. So if you multiply by the complex conjugate over the complex conjugate, you'll find the denominator becomes purely real, and you're able to reduce this rather quickly. And so this makes 0.8 minus J 1.6 ohms. That's the equivalent impedance of these two guys over here. Alright, now we can get the current that goes through this resistor. Call that I. We can use current division. See now, because we've got this current and it splits up between two parallel branches. This branch, the J10 ohms, and then this equivalent branch over here. So we're going to take the current source, 2 angle 0 degrees amps, times the impedance of the branch whose current you do not want, so that's J10 ohms, divided by J10 ohms plus, well, we've got the 1 ohm, and we've got this equivalence as well, 0.8 minus J 1.6 ohms. So you can simplify this current, right? You can combine the real parts together in the denominator, the imaginary parts in the denominator, multiply by the complex conjugate over the complex conjugate, and you find that the current, right, you can get the current then, and if you want the voltage is simply the current times 1 ohm, right? Because we've got the current going through the resistor times 1 ohm resistance gives you the voltage across. So this gives us 2.33 angle 10 degrees volts. So if I transform that back to the time domain, this is 2.33 times the sine, because we started with a sine, current source is a sine there. Sine of 5t plus 10 degrees volts. Alright, again, feel free to pause this. And I'm going to erase this, make some space. This guy over here. Alright. Finally, let's consider only the 5-volt source, DC, right? So at DC, well, first of all, we're going to turn off this voltage source, make it a short. At DC, the inductor is a short also. The current source is open, so I just got my resistor here, 1 ohm. The capacitor is an open, so I've got my resistor there, that's a 4 ohm. And again, here's the 5 volt. Ah, isn't that nice, right? And the voltage I'm looking for is here. Call that V out triple prime. Alright, well notice here the current is going to be going counterclockwise in this loop, so V out triple prime is going to be negative. And what's the voltage across there? Well, V out triple prime is equal to negative 5 volts. I can use voltage division times 1 ohm over 1 ohm plus 4 ohms. So that's nice, that's negative 1 volt. So I've got my 3 contributions. So in the original circuit, with all 3 sources on, V out is simply V out prime plus V out double prime plus V out triple prime. That is 2.498 cosine 2t minus 30.79 degrees plus 2.33 sine 5t plus 10 degrees minus 1 volts. There's the answer. Okay, now we're going to move on to source transformation. Source transformation. So I'm going to erase the circuit and the work. Again, feel free to pause the video if you need to. Alright, well let's review the goal of source transformation for DC circuits. Recall in DC circuits we had a voltage source, V, and in series with a resistor, R. And presumably it's connected to something. And we asked the question, can I transform that into a current source in parallel with a resistor? Call this RV for the voltage source resistance, and RA for RI, I guess, for the current source. So we asked the question, can I do this transformation so that everything external to this thing and external to this thing then remains unchanged? So all the voltage outside of this universe and all of the currents outside of the universe here of this little dashed circle remains the same after the transformation. Can I do that? Yes. Yes, we showed that you can do that, and the reason you would want to do such a thing is after the transformation you might have something over here like this, and so you can combine, maybe this is Rx, you could combine Ri with Rx, and over here you would not be able to do that because Rx is not in series with Rv, and it's not in parallel with RV, but over here, once you transform it, Rx is in parallel with Ri, so that allows you to combine things and start simplifying the circuit. That's why we did that. So we're going to look at something very similar here in AC circuits. So in AC circuits, consider a voltage source, V, in series with an impedance. We're going to call that ZV for voltage source, connected presumably to something. Okay, and we want to know, can we transform that, right, to a current source? Call this I in parallel with an impedance, call it ZI, right, such that everything outside of this universe, right, outside of the dashed circle, remains unchanged. All of the voltages outside of the universe, outside of the dashed box, remain the same. All of the currents outside the dashed box remain the same. Can we do this transformation? Yes, we can. Alright, so now I want you to consider a connection. Call this ZL for load. Right? And the same connection over here, ZL. So ZLs are equivalent here. So as soon as I make that connection, I get a voltage across that. We'll call it VL for load, and I have a voltage across here, VL. So if these are to be equivalent pictures, if the transformation is to be equivalent, then the voltage across the load, because the voltage happens external to the dashed box, has to be the same in both cases. No matter what I connect, no matter what ZL is, the voltages have to be the same in these pictures. And, okay, we're going to draw some current. Call this IL. And again, if this is to be an equivalent transformation, no matter what I connect ZL, if I connect it here and if I connect it here, I should draw the same current through that load if this is to be an equivalent transformation. Alright, so now consider a very special load impedance. Consider ZL equals infinity, an open circuit. Okay, I'm gonna call this picture A. I'm gonna call this picture B, so I can reference them. All right, picture A will look like this now. All right, and let's ask ourselves, how much voltage is across that open circuit now? VL. Well, there's no current that flows, right? Cannot be any current there. So there's no drop across ZV. So there's no drop across this impedance, and so our open circuit voltage is exactly the source. Now let's consider picture B. And remember, we said that if I connect the same thing, so I'm going to connect an open circuit here, I have to get the same voltage. All right, well, how much voltage do I get in picture B? The current I of t comes up through to the top node, and it can't go right through the load because the load is open, so it has to go through Zi. So according to Ohm's law, the voltage from top to bottom then is I times Zi. And again, these voltages VL have to be the same. So I'm going to write that here. If I equate those two, I get V of t equals I of t times Zi. Okay, and we'll come back to this in a second. But now let's consider another special case for the load impedance. Consider ZL equals 0, a short circuit. Right? In picture A, I'll have something that looks like this. ZV connected to a short like that. Right? Now the voltage across the short is 0, but this is going to bring some current. Call that IL. Now in picture B, connect the short. Again, the voltage across that short is 0, but that's going to bring some current IL. Over here in picture B, that short is shorting out because it's in parallel the impedance Zi. So this brings all of the current I of t. Right? Over here, we can use Ohm's law to find IL. We've got voltage V of t across impedance ZV. So the current is V of t divided by ZV. Right? And again, if this is to be an equivalent transformation, the currents have to be the same. So V of t over ZV equals I of t. Or V equals IT times ZV. So now I compare this result in red in the box with the result in the blue box. Okay, those both must hold. So if those are both going to hold, it must be true then that the two impedances in the pictures, ZV over here and Zi over here, are equal. That must be true. So let's drop the subscripts and just call it Z, okay, in both cases. Further, the transformation then, the relationship between the voltage source and the current source is given by then either one of these red or blue boxes. So V, the voltage source, is equal to the current times that Z. So if we have this picture on picture A and we want to go to picture B, we say, well, the I is going to be V divided by Z. And if we have picture B and we want to go to picture A, we're going to say that V is I times Z. And we've already found the relationships between these two, they're equal. Okay, so let's be more clear about that. Let's be more concrete. So if I have this picture, or this building block. This is a basic building block of our circuits. I can instead draw this picture, but the current here is V of t over Z. Okay, so that transformation works. If I have this picture, I, in parallel with Z, I can transform that into this picture where this voltage is I guess we're calling it I of t, excuse me. Let's go back to this picture here. We're calling it I of t. I of t. So if I have this picture, I of t in parallel with Z, then I can transform it into this picture. Voltage source I of t times Z in series with Z. Like that. Okay, let's look at an example of how we can apply source transformation to simplify a circuit. Right. Let's say we start with a voltage source that is 20 angle negative 90 degrees volts. And it is in series with 5 ohms. So there's our building block. Then we've got 3 ohms here and an inductor of 4 ohms there. Excuse me, that should be J4 ohms, the inductor. Then we have a 4 ohm resistor and a capacitor of negative J 13 ohms. And then a 10 ohm load. Okay, and I want to find the voltage Vx there. So I'm going to use source transformation to find Vx. Okay, so as we said, here's our building block, and I can transform that into a current. So here's I, and the I is going to be 20 angle negative 90 degrees divided by 5 ohms. So that makes 4 angle negative 90 degrees amps. Then the 5 ohms is in parallel now. So this is still 3 ohms. This is still J4 ohms. 4 ohms. Negative J13 ohms. 10 ohms. And because that's equivalent, everything out of that universe has stayed the same, including Vx. Now, the 3 ohms here and the J4 ohms are in series, and that combination is in parallel with the 5. Right? So we can combine that. So this guy here makes, okay, we'll call it Z1, and that's going to make the product over the sum. So 5 times 3 plus J4 over 5 plus J3 plus J4. So over 8 plus J4 ohms. Alright, so now we have this current source of 4 angle negative 90 degrees amps in parallel with this lumped equivalent resistor of this thing. Okay, this comes out to be, by the way, 2.5 plus J 1.25 ohms. So this is our impedance that is in parallel with the current source. So we can transform that back now to a voltage source. Okay, and the value of the voltage, let's call this Vs. Vs is that 4 angle negative 90 degree amp times 2.5 plus J 1.25 ohms. Right? This is equal to 5 minus J 10 volts. So I'll write that up here. Instead, I'll say Vs equals 5 minus J 10 volts. Or, yeah, we'll keep it like that for now, but you could turn this into magnitude and phase if you like. Okay, and then remember, we move the Z1 back up in series with that. So Z1 was 2.5 plus J 1.25, so the 2.5 is the real part. That's like a resistor, and it's a positive J, so that's an inductor. J 1.25 ohms, right? And then we have the 4 ohms, the negative J 13 ohms, and 10 ohms. And again, everything outside of that transformation remains the same, so that's still Vx there. Alright, now we have a big series circuit, right? So we can get voltage, we can get Vx with voltage division. This is why source transformation helps us. So we end up with a topology that's simpler to solve than what we started with. So Vx equals the voltage source 5 minus J10 volts times 10 ohms, the impedance whose voltage we want, divided by, I'm going to draw a long bar there because we want the sum of all of the individual impedances. So the real part would be 10 plus 4 plus 2.5. So that's 16.5. Okay, I guess I didn't have to draw the bar so long. Okay, then the imaginary part is J 1.25 minus J 13. So that's minus J 11.75 ohms. Alright, so we carry out that multiplication and we get Vx is 5.519 angle negative 28 degrees volts. Alright, and finally, last but certainly not least, is Thevenin and Norton. Now, just let me remind you of the general idea. You may have some complicated linear circuit. Lots of resistors, lots of inductors and capacitors, sources, and so forth. Most circuits have an output. Okay, the end goal is almost always to interact with the outside physical world. So it's got an output. You might connect headphones to this output. You might connect, an appliance. This this output could be connected to another linear circuit, and so on. The idea is that you don't want to analyze a whole different, you don't want to analyze this complicated linear circuit more than you have to. So if you were to connect one device, call this load resistor 1, you'd have to analyze the circuit to figure out how much voltage and current you're going to get at the load. But then if you change that resistor, if you plug in a different device, load resistor 2, you don't want to have to reanalyze this complicated circuit. Okay, you don't want to have to do that. Well, it turns out Thevenin's theorem says that this linear circuit can be written as a voltage source I guess we've been using the squiggle to show an AC waveform. Any linear circuit can be written as a voltage source in series with an impedance Thevenin, and we're going to call this voltage source Thevenin. Right, so this and any linear circuit can be reduced into this picture. So now, if these are equivalent, again, that concept or that notion of equivalence, now I connect, and these don't even have to be resistors, these can be impedances themselves. But if I connect a load impedance, I can analyze this circuit, right? And I should have the same answer as if I analyze this circuit, the more complicated one. And if I change the load resistor to a second load resistor, now I just have to analyze the Thevenin equivalent of the linear circuit. Right. I'm not going to say too much more about that because you've already seen it. It's just that the Thevenin voltage now has a magnitude and phase, and the Thevenin resistance is not a resistance anymore, it's an impedance. And from source transformation then, if every linear circuit has this picture, then it also must have this picture as well. Any linear circuit can be put into this form from source transformation, right? From source transformation, we know that if we have this picture, picture A, we can transform it to picture B. We know the relationship between the Thevenin voltage and IN. IN is the Norton current. We know that relationship from the source transformation. Right, so this is Norton's theorem. Norton's theorem says that any linear circuit has this form, circuit B. This is the Norton equivalent circuit. Now, if you really remember how to do the Thevenin and the Norton analysis, you will remember there were two separate strategies for if there was a dependent source in the circuit. So remember, the first thing you had to do was ask yourself, is there a dependent source? If the answer to that was no, then we had a couple steps to find the Thevenin equivalent circuit, right? The Thevenin voltage and the Thevenin impedance. If the answer was yes, well, we had a few more steps, and it was much more complicated if there was a dependent source. And so that's actually a little bit out of reach for our class. For AC circuits with dependent sources, the Thevenin equivalent. So we're not going to worry about that. I will not ask you to find the Thevenin equivalent of an AC circuit with dependent sources. So we're only going to look at with independent sources, circuits with independent sources. All right, well, if the answer to that question was no, we had a couple steps, and the first thing we were going to do was turn off all independent sources. And then find the equivalent resistance, and now it's going to be the equivalent impedance. Find the equivalent impedance looking back, so we'll say looking into the output terminals. So in this picture here, the original picture, can you find this equivalent impedance with the sources all turned off? All right, and then, okay, this gives you the Thevenin impedance. Okay, so this was to find the Thevenin impedance. To find the Thevenin voltage, we're going to remove the load and find the open circuit voltage at the output. Okay, so these steps are similar to DC, and so I'm not going to say much more about that. I'd like to look at an example. All right, so let's say we have one voltage source that's 120 volts, angle 75 degrees. Minus J6 ohms, 4 ohms. Eight ohms, and this inductor is J12 ohms, and the output is here. Okay, so let's start by finding the Thevenin impedance, and the Thevenin impedance again is the equivalent impedance looking into the output terminals with the source turned off. Now I've identified the nodes once you short out the voltage source. So we're going to try to find the Thevenin equivalent circuit. We're going to try to find the Thevenin impedance. So the first thing we need to do is short out the voltage source, and once we do that, then this thing, which I've labeled node 0, this becomes one giant node. Okay, then there's node 1 and node 2. And the reason I'm identifying the nodes is that I don't like this diamond shape. Okay, I'm going to redraw the circuit. So let's try that. So I've got my capacitor minus J6 ohms and 8 ohm resistor there. I've got a 4 ohm resistor and a J12 inductor there, and I'm looking for this equivalent impedance. Now, let's observe if I've changed the circuit at all. I better not have. I'm going to identify the nodes by circling them. Alright, so notice here, this is what we called node 1. This is what we called node 2, and this is what we called node 0. You see, the capacitor, for example, is connected between nodes 0 and 1. So that's what I've got in this figure, 0 and 1. On the circuit on the left, the 8 ohm resistor is connected between nodes 0 and 1 as well. And on the right, it's connected between 0 and 1. On the circuit on the left, the 4 ohm and the J12 ohm are connected to nodes 2 and 0. And on the circuit on the right, indeed, the 4 ohm and the J12 are connected to 2 and 0. The circuit on the left, the output terminals are terminals 1 and 2. Circuit on the right, the output terminals are 1 and 2. So yes, this is indeed the same circuit, just rearranged a little bit differently. Alright, now, observe, you can clearly see now that the capacitor and the 8 ohm resistor are in parallel. So we've got 8 ohms in parallel with minus J6 ohms. So we can do the product over the sum, so that gives me minus J48 over 8 minus J6 ohms. If I want to simplify that, I can multiply by the complex conjugate of the denominator divided by the complex conjugate of the denominator. And that gives me 2.88 minus J 3.84 ohms. And now if we look on the right, similarly, we've got the 4 ohm in parallel with the J12 ohm. Alright, so I can do the product over the sum. That gives me J48 ohms divided by 4 plus J12. And if I multiply by the complex conjugate of the denominator over the complex conjugate of the denominator, okay, I can simplify this to 3.6 plus J times 1.2 ohms. So this is the impedance on the left. Call this Z1. This is the impedance on the right. Call this Z2. So now let me redraw the circuit with Z1 and Z2. I'm looking for this impedance. Clearly, Z1 and Z2 are in series. So the equivalent impedance, which is also, remember, the Thevenin impedance, is Z1 plus Z2. So if I add those two guys together, I get 6.48 and minus J 2.64 ohms. So there's half of my answer. I'm trying to find the Thevenin equivalent, so I need the Thevenin impedance. Next, I need the Thevenin voltage. So let me erase some of this, get some space. And I'll keep the answer. All right, now, let me redraw the circuit again. So I'm going to redraw it again because now, to find the Thevenin voltage, okay, I need to remove the load from the output. Well, there is no load at the output, so that's done. And now I need to find the voltage at the output terminals. But the voltage source is back on. Okay, it's the regular circuit now. So I'm going to draw the circuit. (75°) Just going to redraw it like this with nice right angles, right? Everybody loves right angles in circuits. And is scared of non-right angles. So let me draw it with right angles. Okay, nice drawing. And let me label this. This is going to be the Thevenin voltage if I can find it. Alright, let me begin by making this ground, and let's call this V1, and let's call this V2. Now I can find V1 with voltage division, because notice the minus J6 ohm capacitor and the 8 ohm resistor are in series with one another. And I know the voltage across that series combination is 120 angle 75° volts. So V1, the voltage across the resistor, is equal to 120 angle 75° volts times the impedance whose voltage I'm interested in. So I want the voltage across the 8 ohm divided by 8 minus J6 ohms. Similarly, and get V2, right? So this is 120 angle 75° volts times J12 ohms divided by 4 plus J12 ohms. Right, so you do your complex algebra, you simplify V1 and V2, and you notice now the Thevenin voltage, the voltage I'm looking for, is the difference V1 minus V2. So after you do your complex algebra and you get V1, V2, and you do the subtraction, you find that you have 37.95 angle 230°, or excuse me, 220.31° volts. So this is the Thevenin voltage. So this circuit, the original circuit, has an equivalent representation, okay, and that is a voltage source of 37.95 angle, we'll round it to 220° volts, in series with this impedance. So this impedance is 6.48, it's a resistor, and then because it's minus J, that's a capacitor, 2.64 ohms. Okay, and this is again the Thevenin equivalent circuit for this thing. So if we go into the original picture, right, and we connect some load to this thing, RL, and you want to know what the voltage is across RL, you're going to have to analyze this again, or you just analyze the equivalent circuit. Right? That's the power of the Thevenin equivalent. Alright, well, from source transformation, we can get the Norton equivalent circuit. We know that the Norton current from source transformation is the Thevenin voltage, this voltage, divided by the impedance. So this Norton current is 37.95 angle 220° volts divided by 6.48 minus J 2.64 ohms. Okay, so you do your complex algebra and you get IN. Okay, the resistor comes down here, 6.48 ohms. The inductor stays there. The capacitor, sorry, comes down as well. And this is the Norton equivalent circuit, if we want.